Hello everyone. This video is to show you something about using the assembler and the von Neumann machine in our week 6 worksheet assignment, talking about the lab experience 15 exercises. In this lab, we will see how our assembler will be working with a assembly program. And we will see the assembler used to assemble the assembly program, and will scan to find grammar error, that is syntax analysis, and also will help us to find any semantic errors in the program. The first part of the exercise here is about syntax analysis. What we need to do is to start the assembler. Okay, so you need to go to the lab software and click the assembler. And in the assembler, we will open an example. Suppose example 1, this is an assembly program. Here is the source code of the assembly program. And as you have learned, we use start begin to mark out the start of the program, and start end to mark up the end of the program. They are called directives in the assembly program. They are not a part of the assembly code. Okay. And the program is this part. All right. Now we can follow the direction as it says. Suppose we click the assemble. Assemble is to convert the assembly code to the machine code. Okay, after we assemble, in the right side, we can see message. Okay, it just add the line numbers to the assembly program, and will tell you if there's error or not. And right now it shows no error reported. Suppose we remove the dot so that the directive begin is not correct. We assemble it again, and it will report the error. And you can, for your submission, you may do a screenshot for this or copy the error to your work. Okay, this is a record of your lab work. So to correct it, add dot, assemble again, no error. If you remove a keyword like hot, remove the T, assemble, it will show illegal opcode how, and we can find, right, in the source code, so that add T. So here, the assembler show us that if there is any error in the directive or in the assembly code, it will display the error, what the error is. Okay. And this is about syntax analysis, because if there's any error in the grammar, it will show the error, and we can easily find, according to the error, we can find what error it is, right? So that we can find in the source code and correct it. Now, the second is static semantic analysis. Semantic analysis is to see if the meaning of the any element in the program is correct, even though the grammar might be correct. That means there's no syntax error, but there may still have a semantic error. Okay. For example, if we change add y, suppose change to add a, there is no syntax error, and we assemble the code. All right, here is the code from the source, but it also report error, undeclared data label A, because A is not declared anywhere. It is not declared. For other data like X, Z, we can find they are declared X, Y, Z, right? So that means even though the statement is syntactic correct, but no declare character A, and it does not know what to add. So this is a kind of a semantic error. Let's change it back to Y, and we know that there should have no error, right? So this shows us that assembler can help us to find semantic errors in the code. Now the third part is helping us to understand the object code. The object code is the machine code. The machine code is our object for the assembly program, and it can be executed by the machine. All right. Now in this assignment, it has a document lab 0503 and ask you to download. Actually, this is a mistake. Okay. This document is for lab experience 5, not for our lab experience 15. Okay, so just skip it. Now let's see. How can we get object code? In assembler, okay, we can assemble, and we can also view the object code. Suppose click on it, we can see that this is the object code, binary code, machine code of this assembly program. All right. And you can see for each of the assembly statement, we have a machine instruction, right? One by one. Okay. The directive like .begin and .end, they are not a part of the assembly program, so that they are not converted. And another thing is that we can view the symbol table. The symbol table contains XYZ. XYZ are symbols we defined for the assembly program. And the assembler will assign them addresses where they are held in the memory. Okay. Now, we can execute the program. So click execute. Then the von Neumann machine is open. And the von Neumann machine is an architecture that separates memory from CPU, from the central processing unit. And this window shows us that in the center is the content of the memory. In the memory is listed serially from 0, 1, 2, 3, up to its capacity. And the red column / stores the program code, instruction code, and data. And we can find that the instruction code here is what we get, the object code in the assembler, right? And the left side is a set of registers in the CPU. We know that CPU basically contains a arithmetic logic unit. Like this machine has two ALU, arithmetic and logic unit, 1 and 2. It also has a set of other registers. PC is program counter. It always points to the the address of next instruction in the program. Initially, it points to 0. That is the starting of the memory. IR is instruction register, which is used to hold the instruction to be executed. R is general register. It can be used to hold temporary data. CCR is condition code register. Generally, it will have 3 bits. 1 bit record like negative, another record like 0, and another record overflow or something. Some machine may have 4 bits to record the conditions. MAR is a memory address register, which holds the address of an instruction, memory address of an instruction. MDR is a memory data register, which holds the instruction or data in memory. Okay. Here, the right side has 2 panes. The upper one is source code, the source code of the assembly program. And the bottom one is the microcode, which may display some subset of the code or some operations, detailed operations of the instructions. Okay. Now, what do we need to do? Suppose we want to see the detail of operations, so that we need to click check on. Okay, so let's see on, so that we can see more detailed steps. Now, suppose we execute the program. Click the step. Click. Now we see it points to the first instruction. The first instruction is load X, means load the data in memory at memory address X to register R. To execute this instruction, there are more operations inside the CPU. So here it shows the operations. There are 3 phases for executing the assembly program or assembly instruction. The first phase is the fetch phase. The fetch phase is to fetch the data from memory to CPU. Okay. The second phase is to decode the code, decode the instruction. And the third phase is to execute the instruction. Okay. Now the first phase is the fetch phase. Fetch phase fetch load X. The operations include the 4 operations. First is PC program counter will copy its content to a memory address register. Okay. So currently, initially, PC contains all 0. That is, it points to the start beginning of the memory. That is here. The beginning memory address is all 0, is 0. So 0 will be copied to MAR. Initially, MAR is also 0. Okay, click. So that is executed. Because both of them are 0, so there may not look any change. And then fetch. Now fetch, what fetch will do? Fetch will fetch the content as a memory address to register. So that means it will fetch the content at MAR. The content at MAR currently 0. That is this, right? 0, 0, 0. And then 1, 1. So click step. See, the instruction, here, the content at memory address 0 is fetched to MDR. MDR memory data register that hold the instruction or data in the memory. All right. And the next operation, MDR content will be copied to IR, that is instruction register. Click. We expect the content of MDR be copied to IR. All right. See, this is copied to IR, right? And the next operation, PC will increment. That means that PC's content will change to 1. That is point to the next instruction, the memory address of the next instruction. Click step. So PC updated to 1. That is the next memory address. And then it comes to the second phase, that is decode phase. The decode phase is to explain or interpret, all right, because the content of the instruction has been loaded into registers of CPU, so it will decode to allow all the registers to understand what is to do. And then it goes to the execute phase. At execute phase, it will execute the instruction. Currently, instruction is load X. And it contains 3 operations. The first is the address part will be copied to MAR. That means here, the address part. The address part is the write 12 bits, right? The memory address uses 12 bits. The instruction contains 16 bits. The left 3 bits is the opcode. Write 12 bits is the operand or the memory address. So here, the write 12 bits will be copied to MAR. Click, see, right? 12 bits copied to MAR. And then fetch. Click. So fetch means it fetch the data in memory address register. So the address is 101, so it fetch the data at this address. That is 0010. Fetch to MDR to here, right? And then it will copy the content of MDR to R. So MDR, the content will be copied to R. Click. Yes, it copied to R, all right? So this is the execution of the instruction load X. That means the value or the data at the memory address X is here, right? The address 101 here. The content of the memory address, that is 10, is loaded to register R, right? That is all done. And then PC has been updated to the next memory address, that is 1. So it points to the next memory address that hold the instruction add y. We know that 0011 is add. Okay, we can use the opcode and see the machine code and the assembly code. The assembly code is actually a mnemonic of the machine code. So the first instruction is 0000, that is load, right? And the second instruction in the program is 0011. See, 0011 is here, add, right? Now, click step. It will fetch the first phase of the instruction, second instruction. Similarly, it has 4 operations. The PC's content will be copied to MAR. PC's content right now is 1, will copy to MAR, will be copied to here. Click. Yes, it's copied, right? And then it will fetch. It will fetch the data MAR pointed. MAR is here. It will fetch this data to MDR, fetch the data to memory data register. Okay, so click, right? This instruction is fetched to MDR. And then MDR's content will be copied to IR, Click. See, this content copied to IR. So instruction register now has the instruction. And then point counter will increment. That means it will point to the next memory address. That means the memory address for the next instruction. Step, decode, and then execute. It execute the second instruction. It will have 6 operations. The first is the address of IR will be copied to MAR. Address of IR, that is 00110, will be copied to MAR, copied here, because this is the actual address, memory address. Click, see, this copy to MAR, right? And then it will fetch the data from the memory address where MAR hold, fetch to MDR. So it will fetch 110, that here, fetch this data to MDR. MDR right now is this, right? It will become 100 in MDR. Click. Yeah. Here this data is fetched to MDR. And then the content of MDR will be copied to ALU1. Content of MDR will be copied to ALU1. Click, right? It's copied here. And then the content of register will be copied to ALU2. The content in register R hold the data we loaded in the first instruction, right? Click, see, R will be copied to here, right? And then it will add the content in ALU1 and ALU2. It should add ALU1 and ALU2, and the result should be stored in ALU1. Click, right? So this is the result of the add, of the addition. And then the content of ALU1 will be copied to register R, copied to here. So content of this will be copied to here, right? So here is the content of R. This is the sum or addition of the 2 values we just get. One is from here, this address. Second is here. So we add up these two values, and this is the result. And now PC point to the next instruction that is here. This instruction means store Z. That means we'll store the data, the result, to address Z to here, 111. Right now it's 0. I click. All right, it first fetch the instruction, store Z. Okay, similarly, PC content, that is memory address, copy to MAR, copy to here. It copied. And then fetch the value in MAR. MAR is here. It will fetch this is instruction. Fetch to MDR. Fetch to MDR. Okay, it is fetch to MDR. And then MDR's content, that is the instruction, be copied to IR, copied to instruction register. So MDR is to be copied to here. It's copied, right? So this phase, we fetch the instruction from the memory to IR. And next we will decode in the CPU and then execute. Execute phase contains 3 operations. First is the address part of IR, copy to MAR. Address part of IR, that is 00111, copy to MAR, that is the address pad, copy to MAR. All right, copied. And then the content of register will be copied to MDR. Content of register R will be copied to MDR, copied to here. Yeah, it did. Okay. And then it store, click store, see what happened. It should store to the address that is Z. Yeah, currently memory address register point to here, Z. So the value should be stored here, right? The result is stored here. And then it points to the next instruction. The next instruction is output the value of Z, that is address here. Output this value. The output will be displaying here. Now, first, also fetch phase, similar to actually about the same as we did before. Okay, so we just see that the content of Z here should be fetched. It should be fetched to MDR and then RZ. Here, 110 should be fetched to MDR. Here, this content out this fetched to IR. And decode, and then execute, and see what happened. The address of IR will be copied to MAR. Address pad of IR will be copied to MAR. Okay, and then it fetch the data in MAR. MAR is 111 here. This part will be fetched to MDR, right? And then the content of MDR will be sent to output. Yeah, content of MDR sent to output. That's all. So the PC point to the next address, that is hot. Okay, this instruction 111 is hot. That is stop.
click